Okay, so let's get started. All right, so this talk is called Scalable Automatic Machine Learning in H2o. And so we're going to talk a little bit about what automated machine learning is. What does that term mean? And then we're going to show you how to do it with H2o. So, and by the way, my name's Erin Liddell. I work at H2o as a machine learning scientist, which means I'm making the algorithms that you see here. And the AutoML project is like the main thing that I work on now. So yeah, this is all stuff that I've created. There's two other people that I work with on this, named Ray and Navdeep. And yeah, so this is our sort of solution to automating machine learning. Okay, and I'm just gonna briefly let you know, like, what is H2o, because that's kind of the framework in which we're talking today. So H2o is also the name of a company. So that's the company that I work at. And it's also the name of our platform that we put out. So H2o, the company, has been around for about 5 years. And the main product that we have is this open source machine learning platform, although we are starting to do other products as well. And we're in Mountain View, California. And the software, essentially, I'll go into a little bit more detail later, but it's open source software, so you can just very easily download it and use it on your laptop or on a cluster. And if you are familiar with any of these languages, then you can use H2o, so R, Python, Scala, Java. And then if you're somebody who'd prefer to just work with a GUI, like a graphical interface, then we also have a web interface for H2o. And you can do all the same stuff, basically, in the web interface. And the whole point of H2o is because, back in the early days of, big data, like in the 2010s, the early 2010s, there was all these new big data platforms, like Hadoop was kind of the big one at the time, and a couple years later, then Spark became very popular. And there wasn't good machine learning libraries for these big data platforms. So all of the machine learning libraries that were available at the time were just something you'd run on your laptop, or you can run it on a cluster, but the idea is that you have a single machine that you're working with, and everything happens like in memory on that single machine. So if you have a data set that's like a billion rows, that might be a big data set. So you might have to, you can't maybe fit a billion rows of data into the memory on your laptop. So what you have to do is distribute that data across a bunch of machines, and that's what H2o does. So you just give it your data set, it knows how to distribute the data across machines, and then it knows how to do machine learning across that distributed data. And so the real, technological feat that H2o accomplishes is being able to do machine learning where you don't have the whole data set in memory all at once. And you have to change the way that the algorithm works so that you can actually do the machine learning part. And that's what we do. And I guess the other focus is, because a company made this software, is we care, and sort of our customers are companies that pay us for enterprise support. So they care a lot about like putting these models in production and sort of that aspect of things. So once you've trained the machine learning model, then like, what do you do with it? So if you use some of these other open source libraries, they don't have often like a good solution for taking that model and putting it in production. So that's another thing that H2o focuses on, is productionizing the models. Okay. And these are just three scientists that we work with. So if you're familiar at all with the machine learning space, the first two guys wrote a book. It's called The Elements of Statistical Learning. Now there's another book that's, I forget the name of it, but it's like the more introductory version of that book, and that's free PDF. So if you go to their website, you can read it. So that's kind of one of the main textbooks in machine learning. And so these are the authors. They're at Stanford. And the third guy, Stephen Boyd, is also sort of in the machine learning community as well. Okay, so that's a little bit about what H2o is and what the company is. So what we're going to talk about today are these things. So what is automatic machine learning, and what does that mean? And we're going to talk about one particular subset of AutoML, which is called Bayesian hyperparameter optimization. Now try to say that fast, like 3 times. It's a really hard word to say. So then the next thing is the topic is random grid search and stacked ensembles, and that's the approach that we've taken in our AutoML. And you could combine all these things together. These are just different sort of techniques at automating the training of machine learning models to get a good result. And then again, I'll introduce the H2o machine learning platform at like a little bit deeper level. And then I will show you how to use it. So if you brought a laptop, you're free to I'll point you to where the code is, and you can kind of go through the code with me if you like. Okay, so what does AutoML mean? Okay, so there's lots of different pieces of AutoML, but the real goal is to reduce the amount of work that the human has to do, basically, the data scientist. And there's a lot of things involved in training models in machine learning. You have to have some idea about like what the algorithm that you're working with, how it works, what are all the important hyperparameters, what values do they need to be set at? Because basically what you do when you train a machine learning model is you can imagine just like a big board with like a lot of knobs on it, and you just have to keep turning those knobs to different values until it's like the precise like setting that like makes the best model. And it's all dependent on like whatever your data set that goes in, like the knobs will be different, or the best values of the knobs will be different. So part of what a data scientist does is either just manually tweaking those knobs based on their own knowledge of what worked well in the past, or using something called a grid search, where you just put a big list of values that you try, and you kind of try every different combination of all the different numbers, and you just pick the best model that way. So that's the goal, is to have a process that can go off and sort of automatically tune these knobs for you. If you either don't have the knowledge to do that on your own, or you just don't want to do it, because I can tell you that after you've done that at like 1 million times, it's not fun anymore. The like 900th model that you've trained, you're like, okay, I just want to have this do itself, and I don't, I've learned everything I need to know about this type of model. I'm just over it. So, and it will save you a lot of time. Like if you're a data scientist, you can spend time doing other things, or you can just use this as like a first pass, and like it'll get you a pretty good model. And then if you want to then fine tune it later, that's another way to use it. So it's not just for people that like don't know how to do machine learning. It's really for people that appreciate the value of automating things. So I basically built this tool for myself. Like I want something, I got sick of writing all the code 100 million times. So I just thought, like, what is my process of what I do when I'm trying to get like the best model? What are all the things I try? Like, how do I try them? And just wrap that into a big function and just do it automatically. So, all right, so that's the goal of AutoML, is to automatically find a good model. So there's different parts of that. So you can kind of break it down into these 3 major categories here. So data pre-processing is something that you have to do with machine learning anytime. It's not just AutoML. So, so we can automate that a little bit. So some of these words might not mean anything to you if you're not super familiar with machine learning. So there's imputation, which just means anytime you have missing values in your data, you have to deal with that. So either there's some algorithms that can handle those sort of automatically, but most of the time you have to fill in the missing values, essentially. The exception is any tree-based algorithms. There's ways to kind of ignore that. Then there's something called one-hot encoding. So anytime you have categorical data. So if your column in your data is something that represents a category, like the type of animal, and it's like cat, dog, or pig, or like the 3 values, then you can in H2o give that to the model like as is, and it will do something under the hood. But what it's doing is something that's called one-hot encoding. It basically takes categorical data and expands it into numeric columns. So if there's 3 categories, you're going to end up with 3 binary columns, 1 for cat, 1 for dog, 1 for pig. And if the value was pig, then the numbers that go in there are 0, 0, and 1. So that's how you're encoding that. You're saying, was this a dog, yes or no? 0 means no. Okay. Was this a cat, 0 or 1? 0, because it was not. And then you go to pig, and then you put a 1 there. And it's a way to turn like categorical data into numeric data. Because machine learning algorithms understand numbers. They don't understand like abstract concepts. So this is how these are kind of some of the things that you have to do to like get the data in the right format so that the machine learning algorithm can understand it. The good thing is that we do all this for you in H2o, so you don't have to actually learn it if you don't want to. A lot of other libraries, you have to do that yourself. That gets old pretty quickly. And then standardization in some algorithms, you have to sort of what's called normalize your data. Okay, so these are all things that you kind of just have to do regardless of if you're doing AutoML or not. Okay, so there's other things that you can do. There's something called feature selection. So maybe you have a lot of columns that represent like things that you have measured in your data set, but like most of that is noise. Like, maybe it's just going to confuse the model if you put all that in there. So you want to kind of like trim it down to just like the good data. Generally, I wouldn't recommend doing that. I kind of like to have the algorithm handle that on its own. But feature selection is called when you subset the features to like good ones, basically. And then feature extraction is another word that's a little bit different. It just means, given your original data set, can you like extract some new knowledge from that? And there's methods to do that. So all these are things that like enrich your data and make better models. And then there's some other things that are called like count or label or target encoding. I'm not going to go into what that is, but this is another way to get like more value and more predictive power out of your categorical features. Okay, so there's all this data stuff that you can do to help your models to begin with. And then basically in any sort of AutoML process, you generate a whole bunch of models. That's part of like what a data scientist does. You don't just know in advance what the best model is going to be and you train it once. You kind of just go through and do a whole bunch of different models and then eventually pick like the best one. That's kind of what I mean by model generation. So there's different ways to do that. One is called grid search. So if your model has like 3 what are called hyperparameters or knobs, then you might say, okay, I want to do a random or just a grid search over these 3 knobs, and I'm going to try all the different combinations of these different values. And so that's essentially iterating over all those combinations is called a grid search. And at the end, you end up with like a bunch of models. Let's say you have like 3 options for one parameter, 2 options for another, and 4 options for another. The total number of combinations is like 3 times 4 times 2, and whatever that is, that's the total number of models that you'll end up training. And then at the end, you just pick kind of what the best model out of that group is. And that's a way to kind of, like, you're finding the best parameters just by trying all the different combinations. But that's very computationally expensive. So you could try, like, every possible model, but then you're training, 1 million models, and that takes forever. And, so we try to think of, like, smarter ways to do that. So one thing is basically do that except for randomly sample combinations, and you just get a random sample instead of the whole exhaustive search. So that's called random grid search. And then another technique is called Bayesian hyperparameter optimization. And the gist of this is that you kind of start off with a model, you train it, you measure the performance, and then you use some other model that's going to tell you what the next set of parameters that you should try is. And so then you try those, you report back to the other model and say, okay, I tried your parameters, here's the performance of that, and then you give that data to that model, it tells you a new set, and you kind of go back and forth, and that's, yeah, question?
Why is it Bayesian?
So Bayesian is kind of like a fancy word for having prior knowledge about something. So the way that it's used here, it just means like you're using the information about the previous models that you just trained and how they performed as like to inform your next decision. So that's kind of why it sounds like fancier than it is. It's basically just like we looked at some previous results and then incorporated that into our model and then use that to make new choices. So I'll talk a little bit more about that. And then another thing that you can do is you can what's called tune a model on a validation set. So in machine learning, you usually have a training set that trains the model. Then you have a test set, that's where you test the model. But there's also this third set that you can use that's just used for like what we call tuning the model. And tuning the model just means playing with the knobs until it looks good. So the way that you use the validation set is you turn the knob a little bit and measure how it did on the validation set, and then you turn in the knob a little bit this way and measure, measure, measure. And then you kind of like waste that data in your training process. So you kind of have to get rid of it. You can't use it again to test the model because you've already incorporated that data into your model. So you have to kind of throw it away once you're done. And then when you test the model on the test set, that's all data that you've never seen before. So when you test the performance, it's like an honest evaluation of your model. Okay, and then the last thing is once you have a bunch of models, one thing that you can do to improve the performance is called making an ensemble. So you combine the models together into like a, sort of like a group think. It's like, on like those shows where you can like ask the audience, and then like the audience might not be very smart individually, but if they like collectively, they kind of like get a good answer. That's like ensembling, basically. You're like, okay, individually, most people like don't know what this is going, but if you ask enough people and you average the results together, then you kind of get a good answer. So averaging is just one way to combine models. There's other ways, and that's one of the ways that we'll talk about is called stacking. And it's also called super learning, but that is primarily a term used at Berkeley only. So if you hear that word, it probably means you're in Berkeley. Or there's people who are from Berkeley that are now at Harvard that also use that word. So it's the same thing, stacking or super learning. And then there's another type of ensembling called ensemble selection. It's a different way of doing it. It's kind of like a greedy approach to ensembling. You keep adding models until the performance stops increasing, and then you stop. Whereas stacking is you actually just give it all the models, and then it learns the best combination. So if there's models in there that are bad, it should learn to ignore the input from those models. So it's kind of just a different way of arriving at an ensemble. Does anyone have any questions so far? This might be a lot if it's your first machine learning talk, but yeah.
Is there any particular reason in general to use stacking versus ensemble selection, or is it more just preference or trying things out?
That's a good question. I think it can depend a little bit on like what your situation is. If you have a huge number of models versus a small number of models, like if you have only like 5 models, then probably stacking is, you might end up getting like similar results either way. It's probably always good, like in any machine learning process, to try both things and see what works best for your data. There's not as much software that does the latter one, so it's in machine learning, it's mostly about availability of what's easy to use and what's there. So we have implemented stacking, and maybe a little bit later we might do the other one as well. But yeah, so probably just if your software has it, you should try it. If not, probably don't want to write it up yourself unless that's the kind of thing you like to do.
I have a question, but I don't want to rat hole. But I was in a situation where I created like a specialized training set with a specialized model to create a submodel, which was used as an input for which had other data which wasn't as well curated, and it worked really well.
Okay, so yeah, that's another technique.
And then when my colleague at the time who didn't know any better took my features and directly used them in the overall model, and discovered that they totally ignored all my features.
Oh, really?
Yeah, it was very
interesting. Yeah, I mean, you can do all sorts of things. So sometimes if your data is kind of like a mishmash of a bunch of data sets together, so let's say you have run like a web company and you have user data, well, all the data from one user is more similar to itself than it is to like other users. So sometimes what they'll do is create models just on like some subset of the data. So you create individual user models, and then that maybe gets fed into like an overall model or something like that. So usually when you end up doing something like that, it means that all the rows in your data are not like equally what we call IID, or basically independent observations, independent and identical observations. So yeah, that's something to look out for.
So would you use stacking in that case, or the ensemble, or do you think?
I would always go to stacking because that's what I'm more familiar with. So that's not necessarily the right answer, but that's what I would do. Okay, so yeah, these are all different things that you can do to, the goal is always to get the best model. So actually that's not always the goal, but sometimes it's to get the most interpretable model. So maybe you just want a model that you can understand, like a decision tree or a linear model. So I shouldn't assume that that's always your goal, but typically, your goal is to get the best model. Sometimes you have operational constraints, like you want it to be able to predict really, really fast. If you're running some sort of web business and you need sub-millisecond prediction time, you might not choose a big ensemble because you have to generate predictions from the individual models first and then combine them, and it takes longer. But for most people or most use cases, you're not in that situation where that timing matters so much. It's just certain productionized use cases. You might choose to go a different approach. Okay, so all right, so we'll talk about this Bayesian optimization of hyperparameters. But this is probably a little bit technical, and I'm just including it in this talk because it's an important piece of AutoML. But if you're sort of new to data science, you can just kind of tune out for a minute, or you could try to understand, but it's a little bit complicated. So basically what it does, so this is kind of the formal definition of it. So you develop a model or a statistical model of, basically you want to create a map from the hyperparameter space to the what's called objective function. So this is like, in machine learning, you always measure your performance using some loss function or error function or whatever. So the formal term for that is an objective function. So you can minimize or maximize or whatever it is that you have. So maybe mean squared error is something that you can measure the performance of a model with. This will all depend on what type of model this is. Is it binary classification? Is it regression? Some of these metrics only matter in certain cases. So basically what you're doing is you're creating a function that can take as input the hyperparameter values and then sort of predict what the performance of the model would be. So that would be like the ultimate thing to have, because then you could just put in, you know, what you think it's going to be, and it can predict. You don't actually have to do the model training part. So that's kind of the goal. And then there's different ways that you can do it. These are some of the names of the approaches, or, you know, so if any of this stuff looks interesting, you can go into it. Sometimes people call this sequential model-based optimization, because it's, if you remember how I described the process where you train a model, you report the results to this other model over here. It tells you something new to try. You try that, you report back. So that's a sequence of events. So this is not happening in parallel. So this is one of the drawbacks of this method, is you can't just have a big cluster and like try a bunch of models and then be done. You have to wait for them to train in sequence. So this takes longer, and that's probably the main drawback of this. But otherwise, this will get you to the best model in fewer iterations than if you were to just try a massive grid search. So the benefit of a grid search is they're independent from each other, so you can just train them all at once and be done in like one step if you have enough computing power. So just kind of depending on your setup, you might choose one approach over the other. Okay.
With this sequential-based model, is there something like a gradient descent kind of thing, where you try to see how far away you are?
I would say it depends on like which approach you're using, and it's kind of what you call these like surrogate models. They're like, when I say you send the results to the other model, that's what we're calling that, a surrogate model, and it just kind of like figures that out. So there's all different approaches. So it's the way that I'm describing it is like it could include all these different approaches. So yeah.
Kind of new to this. Can you give a real world example of where this kind of starts?
Well, this is just a technique that people use to train their models. So it could apply to anything really. So if you just have software that does this, then you can do it on your model. So I think on the next slide, this is a list of some of the software that does this stuff. So if you're an R person, then there's a very new package called MLR HyperOpt. That's sort of a higher level wrapper to this other one called MLR MBO. There's, if you're an R person, there's a package called CARET, C-A-R-E-T. It stands for Classification and Regression Training, I think. And then there's another package called MLR, and these are like the R equivalent to scikit-learn. So it's just a package, or H2o, like a package with a whole bunch of algorithms in it and kind of a common interface to all the algorithms. You can try a whole bunch at once. And it also has other stuff built in to do grid search and model evaluations. These are like toolkits. So all of these, or these two, are built off of the MLR package. I don't think there's anything like that for CARET package. I could be wrong, but I haven't seen anything. And then in Python, there's a whole bunch of different ones. Some of them are good, some of them are really slow. So again, one of the issues with this is that it can be very slow. So I think I've heard that Spearmint is quite slow, but maybe try one of these other ones. There's a Java thing, and then there's a SaaS tool called SIGOPT. That's a San Francisco startup. And they have an API service that you basically do that process that I mentioned. So you train your models locally, you report back the results. The SIGOPT service will figure out what the next best set of parameters is that you should try, and then you try them and you kind of do that loop over an API service. But that, obviously, you have to pay for that. So if you just want to try it out, try one of these other things. So yeah, that's kind of an overview of that technique. It's not very in-depth, but so we'll talk about this other version. So the goal with Bayesian hyperparameter optimization is to get like the best model for like a single algorithm. So you're like, I want the best random forest that I can get, or the best GBM. So the goal isn't really to get the best model in general, which could be an ensemble or something else. It's just like you want to get the best version of that single model is kind of more the goal of that. And but on the flip side, you can get often the same performance with doing a different technique, which is training a big random grid search and ensembling all the models together. So this is the approach that we take in H2o. So this is what I decided to build because this is all stuff that we already had in H2o. So I guess start with what you have, and then maybe we'll do some of this other stuff at some day to improve the AutoML. So the goal was first to build the best AutoML with what the tools I already had in H2o. So we have random grid search. You can apply that to any model. So, and we also have what are called stacked ensembles or stacking or super learning. So why do we do these two things together? Well, so stacked ensembles, the way that they do well is if they have diverse sets of models. So you might have heard that like in tech there's not enough women, and so you get these very homogenized teams of men, and then they've actually done studies that if you diversify your team, you get better results. Same idea here. So so it's just always a good idea to have diversity in all ways. So this obviously proves that. So anyway, ensembles do well when they have diverse inputs because sort of the idea is like when one model's not doing well, the other ones kind of make up for it. So you don't really know in advance like what your data is going to look like or what type of model is going to be the best for your data. And it might even change within the data set itself. So some row of data might do better with the random forest prediction. Some row might do better in the deep neural net. So if you only work with one model, you're kind of choosing the model that does best like on average for all the rows. But with a stacked ensemble, you can kind of like use the best model on a per row basis, basically. And that's kind of what happens internally with the stacked ensemble. So, and so the more diverse models that you include in there, the better. So one way to get diversity in your models is just to train random models. And what I mean by random models is just pick random hyperparameter values and train a model. And then pick another random set and just try a whole bunch of things. And so individually, maybe those models aren't that great. Maybe you find one that's like really good out of the bunch or a couple that are really good. But it doesn't matter. So you just put them all in the ensemble and you let the ensemble figure out what to do. So this is kind of more formally what's going on. So this, so the ensembles perform well if the models themselves are good and if they make uncorrelated errors. So if they're kind of different models or diverse models, then what's really going on underneath is that the errors that they make are uncorrelated. If you've taken any statistics class, you might know what the term uncorrelated means, but it's not really important. You just have to know that like put in a whole bunch of different types of models, random forest, GBM, even within like the GBM or random forest, try a whole bunch of different parameter settings. And then what's happening is, so stacking uses another machine learning algorithm actually to learn what the best combination is. So that's what machine learning algorithms are good at. They're good at learning things. So you give it a whole bunch of examples of like, how these models perform essentially, and it learns how to like, if you're using just a linear model as the meta learning algorithm, then it would be learning a nice linear combination or weights. That's often what people choose for that what's called meta-learning algorithm, but you can use GBMs, those do well. Random forest. It depends like how many models you have, like if they're good or bad. Like, so you might want to play around with different meta-learners, but you can't actually do that yet in H2o. So we're adding that soon, but right now it just uses a linear model. So I'm just going to explain this, and you don't really have to know how this algorithm works, but it's, you know, I guess since we're recording, might as well just get it on film and share it with other people. You know, it might not be that interesting to you in the room, but so I'm just going to explain like how the superlearner or stacking algorithm works, because it's actually fairly simple. So what happens is, this is basically the setup of any machine learning problem. You have the training data looks like this, X, sometimes we call that X. So the number of observations is N, and then the number of features, we'll call that M, and then you have the response column, we'll call that Y. And so even if you're new to machine learning, this is what you have to know. You have to get your data in this format. So the rows correspond to individual observations or examples, like training examples. And then the features just correspond to different things that you're measuring about the data. So, so if you have a fraud example, so you're predicting like fraud, yes or no. Like let's say you're doing, you work at a health insurance company and you want to predict whether or not a claim is fraudulent. Then you might put in some features that have to do with the claim, like how many previous claims has this person made in the last 5 months, how many have they made in the last year, what type of claim is it, what is their zip code, like all different things that you think might have something to do with the outcome. Maybe sometimes even if you don't think it has to do with the outcome, just throw it in there anyway. And this is how the machine learning algorithm works. It sees a whole bunch of measurements about a particular thing, and then it learns if that thing is a yes or a no in this case. So this is a binary classification. And then once it's seen a whole bunch of different examples, then that's how it learns. So this is your setup, essentially, in all machine learning, all supervised machine learning problems. All right, so with stacking, you start here, and you choose a set of what are called base learners, or you just call them, like those are the models in the ensemble. And let's say you have a random forest and a GBM and a deep neural net and a GLM or something like that, or maybe multiple of each of those. So you start with that, you just decide, I'm going to put these, so that's your job as the user to just decide what you're going to put in the ensemble. And then what you do is you do what's called k-fold cross-validation. And if you don't know what that is, just maybe ignore the next slide. But if you're familiar with what k-fold cross-validation is, it's just a process of training like k models on that data. So you split the data into k pieces row-wise, and you train a model on k-1 parts, and then you test on the holdout piece. And then you rotate which one is the holdout. So then basically you're getting, k models, and then you're averaging the results. So it's a little bit better than just training on one piece of data and testing once. Because if you average over a bunch, you probably get a better result, or a better look at your whole data. So anyway, one of the things that you get when you do k-fold cross-validation is that you get these what are called cross-validated predictions. So when you were training, let's say this represents k-1 number of chunks, and this was your test chunk in this case. You trained on this data, and then you made predictions on this one. Well, if you do that k times, then eventually you can fill in this whole thing of all your predictions that you made. So sort of the product of running cross-validation, usually the goal is to get a better estimate of your model performance. But one thing you also get is just a bunch of predictions on your original data. So there's n rows, get n predictions. So you do this for each one of your models. So we said we had like L number of models. And so now actually you can stack these, and that's I think where the stacking term comes from. You like squish them together or columbine them together into this new matrix. And then this is the setup for the meta-learning algorithm. So if you think about, if you train a machine learning algorithm on this data set now, what is it doing? It takes as input the predictions from the other models and tries to predict the output. So now you have this like combiner algorithm that like knows how to take the output from the models and combine that together and then make a prediction. So it's just, that's really all that's going on in the superlearner algorithm. So, it's not complicated, but if it's your first time seeing it and at least like what cross-validation is, it'll still take a couple times to like read it over and kind of figure it out in your head. I think it helps if you have the diagram, but anyway, my point in this is just showing people that some of this stuff is not that hard, so it's just kind of moving things around and doing some stuff. So if that was above your head, just don't worry because it's all downhill from here. Oh yeah, so I probably should have mentioned this earlier. So this was just, you had a question on what is the difference between stacking and ensemble selection. I kind of already explained the difference, but I'll just highlight again. So with ensemble selection, kind of your resulting ensemble is just like the good models only, and then you average the results together. Whereas in stacking, you can put in good and bad models. You don't want to put in like too bad of models, but it's okay if there's some kind of bad ones in there. And then the meta-learner will, it'll learn to ignore their input if it's consistently bad. So when it's combining all those predictions together, it will kind of just say, okay, you guys are going to ignore your input because you've consistently been bad. You don't get to say anymore. So that's the difference. It's just another reiteration of something I've already said.
Is there a preferred algorithm for the meta-learner?
So I mentioned that like we, by default, use a GLM or like a linear model, but GBMs also work really well. So it depends if you have like really good models and like that's only what you have in there, you might want to definitely try a GBM. I think my experience is that if you don't really know in advance what kind of models are going to go in there, the GLM is maybe a little bit more reliable in terms of you're probably not going to get the best results, but you're probably not going to like totally do a bad job. Sometimes I've seen GBMs do a bad job, but I think in general they probably do better than a GLM. But you should just try different ones. And we, like I mentioned, haven't exposed this feature in the H2o Ensemble, but we will, and then it will be easy to try the different meta-learners. Okay, so I kind of want to hurry up, but so I already mentioned kind of what H2o is. And this is just a reiterating what I've said before, basically. So highlights all the points. It works on all different platforms, all different languages, and the way that it's different from most machine learning libraries is that you can run it not just on a multi-core machine and you make use of all the cores, but on a multi-node cluster. So yeah, you have a question? There's a separate project. So there's a little bit of GPU support in H2o, but there's another project called H2o 4 GPU. That's GPU version, basically, of H2o. And that's just getting started, so we only have a few algorithms right now, but that's probably what you want to look at, yeah.
The XGBoost has GPU support.
True, so we have, XGBoost is the name of a package that does, it's really well known for GBMs, and it's a popular package, and so we actually started shipping XGBoost inside of H2o. I don't know when we added that, like in the last 6 months or so. So that has GPU support, and you can use that in H2o right now. But yeah, in general, like when H2o was built, most of what people were using at the time is like, well, sort of built for like commodity clusters, like Amazon EC2, where you pay, very little money to rent these like fairly weak. I mean, they have some nice, good instances, but the idea is like just get a whole bunch of these cheap machines and just run the models on that, and then it's fairly cost-effective to do that. But one of the things I see people that are new to H2o, they make the mistake of thinking they can just like add nodes, and it's just magically going to make your data go, or your models go faster. So if your data is not big enough to require that, you're just kind of slowing it down, actually. Because if your data fits into the memory of a single machine, then you want to use one machine. Because otherwise, you're just splitting up your data, and then they all have to communicate to each other, and it does slow it down. So, if your data is, I think the rule of thumb that we tell people is like if your data on disk is like H2o will require 3 or 4 times that amount in RAM to run the algorithm itself, which is actually fairly low memory compared to a lot of other algorithms. Because there's a lot of other software, they make a lot of unnecessary copies of the data and things like that. So yeah, if you have a 16 gig laptop, then as long as maybe you have your data is less than 4 gigs, you could probably run it on your laptop. So, all right, so let me just introduce just 2 words that we use in H2o because they have to do with distributed computing. So one of them is what we call the H2o cluster. So then that's not like a machine. That's basically this process, this Java process that's running on your laptop or on a cluster. So it's just the name of the process that all the H2o stuff goes on. So all the models are trained in the cluster. All your data sits in the cluster. It's all in RAM. So it's fast. And then there's no limit on the cluster size. So you can just keep adding nodes if you want. And each node only sees some rows of your data set. So you split your data in rows. So that kind of brings us to the next thing. So if you're an R or Python user, like in Python, you're probably used to like pandas data frames. In R, we have data frames, we have data tables, and now we have tibbles, which are another thing. So it's the same thing. So there's rows, there's columns. You can do things, you can subset, you can do whatever to the data frame. It's just, and it feels like you're using, the native language version of these things, but actually under the hood, your data is split across a bunch of nodes. Or maybe if you're just on your laptop, it's just like normal pandas data frame type of thing. But so there's what we call an H2o frame is actually just a regular data frame, but it's split across your machine. So that's just like jargon that you'll need to know. So the first thing you always do in H2o is like you start up your H2o cluster. So okay, so now I did say it's downhill. Now things get a little bit easier. Okay, so these are just the general things that you can do with H2o. So we have what's called supervised and unsupervised machine learning algorithms. So here's just some acronyms. So GBM is gradient boosting machine, RF is random forest, deep neural network, generalized linear model, whatever. We have a whole bunch of algorithms. Then this is all the stuff that I mentioned at the beginning that's kind of annoying in practice if you have to keep writing code for this all over the place. So we do all this imputation, normalization, one-hot encoding. It just happens automatically in H2o. And there's a term called early stopping in H2o, not in H2o, in machine learning in general. So sometimes you have models that are trained iteratively, and so you don't know exactly in advance when you're going to stop. So what you have to do is you take a separate validation frame and you kind of measure the performance as you're going along. And at a certain point, you look at the performance and you decide the optimal time to stop. And it's basically what happens is if you don't do this, you'll overfit your models. So it'll keep learning and learning and learning, and it overfits to the training set because it thinks, basically the goal with a machine learning algorithm is to, it learns from the data, but you don't want it to learn so much that it's not useful on any other piece of data. So what can happen is if you let a model just like learn too much, it gets too excited and it like, I don't know, it overfits the data. That's the term that you should know. But so we have this thing that's called early stopping, and you just use this holdout set and you kind of measure and make sure that it's doing okay. Because the point at which your validation error starts to go up again, it means that your model is starting to overfit. So that's why we have this extra piece of data. Anyway, you can do that automatically in H2o. This is one of the more advanced, kind of tricky things in tuning a model. So it's nice to have some help doing that. And then all this other stuff like cross-validation, grid search, random search, we have all that. And then once you've trained the model, we have, you can look at the model and you can actually see which variables are important in predicting your features, or your outcome. So that's kind of just knowledge gained. It's not necessary to the training, but it's a nice thing that you get out of the model when you're done. And then performance metrics, plots. So the point is it's a general purpose tool that can do all sorts of things. Okay, so now that we've talked about all these other things, let's talk about what is AutoML. Okay, so in H2o, this is the slide from before, but I've highlighted the things that make up H2o's AutoML. So we do all that stuff, imputation, one-hot encoding, standardization. We do that in all the algorithms. It's not specific to AutoML. And then we do a random grid search over a bunch of different types of algorithms. And then within each of those models, we also individually tune them using a validation set so that we do like early stopping. That's what we're referring to there is early stopping. And then we do stacking of the models at the end. Okay, so I basically just said these 3 points here. And then what it returns is, you obviously have all the models that you've trained, but what the AutoML object, one of the things it returns is what we call a leaderboard. So this is kind of from Kaggle language. So Kaggle is a data science competitions platform where you can compete to win money and prizes. And it's like if your model does the best, you win the prize. So, so they have a leaderboard. It's not, the term is generic, but anyway, that's
Go to learn machine learning.
Yeah, exactly. So they have forums and people post their scripts, and so it is a really good place to go if you want to see people in action, kind of like as a fly on the wall, or maybe then you start to learn how to do some of these things. Yeah, and it's fun. So this is what you get back, a leaderboard. You get all the models in sort of an order of how well they did. And okay, so I'm going to just show you how small the amount of code that you have to write to do this. So this is in R. So you load the library, you start the H2o cluster, you import some training data. Maybe it's in a CSV file. It could be in all different formats, but just for simplicity, we'll put it in a CSV file. And then this is the interface, basically. So there's some options that are not being shown right now, but these are the only options that you need to use. So you say, here's my training data. It's in like in an H2o frame. And then whatever the name of your response column. So if this is the fraud example that I was saying, maybe the name of the column is fraud. Yeah, you have a question?
I have a question on the import file structure.
Yeah.
Can you directly connect to a remote MySQL database, or do you have to download whatever the format is and then upload upload it that way, or can you directly connect to a database?
Yes, you can connect to any database that has a JDBC connector, and I think MySQL is supported. I don't 100% know, but it probably is. Yeah.
When you have a large amount of data, what's the process like of getting something out of a database and distributed onto the servers actually doing the computation?
Yeah, so it just depends like where your data is coming from. So one thing, like in order to be able to do all these computations in memory, you obviously need to get the data from disk or from wherever it is into the H2o cluster memory. So sometimes that can, like if you have, you know, a billion rows, that could maybe even be the thing that takes the longest, is just importing the data into the cluster. So if you, let's say, so this particular file or function right here, import file, is a parallel reader. So if you can take advantage of, you know, all the cores on your machine, you can read the, you know, all the data in all together. It's fairly fast. So I guess, I don't know if I answered your question or not. Did I?
For example, could you just have the cluster pull rows out of the database directly?
Yeah.
Okay.
Yeah, so there's, I haven't worked with that a lot myself, but we have I'll point you at the end to like where the H2o documentation is, and there's a page that says, here's all the different ways that you can get H2o, or get data into H2o, and it will explain, like, here's how you do it if you have a database, here's how you do it if it's on S3, or if it's in a Hadoop file system, or whatever. So yeah, so we try to support like all the popular formats and ways that people have data. Yeah?
Just a quick question. When you created this automated machine learning pipeline, did you make any underlying assumptions about the data you might see? Like maybe you're more biased towards like sparse data, or like more rich data matrix or something?
Yeah, so that's a good question. So one thing when you end up choosing different types of algorithms is if your data is very dense, meaning it's just a bunch of numbers, and versus sparse, which means it's still numbers, but a lot of them are zero. So one of the ways that you get sparse data is if you encode text into a matrix format. So the most simple way that people do that, and they generally do something more complicated, is they take their, you know, let's say you're doing want to do a tweet predictor, like to predict whether or not the tweet, you know, was from Donald Trump's cell phone or his staff's cell phone. So somebody did this kind of funny analysis where they looked at all Donald Trump's tweets, and you can, from the Twitter API, it says the client that was used, so it was an Android versus an iPhone, and so they knew that, I guess he had an Android and his chief of staff had an iPhone, and so you could train a model to see, like, and to predict which one, because that's the label basically, is like Android means Trump, iPhone means whatever, and then they showed like that his tweets were like kind of crazy, or, you know, compared to the more subdued ones. So, so anyway, text. Yeah, that was a side note. But so what you would do is you take all the tweets and gather all the words that ever appeared in all the tweets, and then you sort of line them up on as the columns of the feature. So each word that exists in your sort of dictionary is a column, and then everything's zero except for where that word occurred in that tweet. So if the tweet is only 5 words long, then you have all zeros except for in 5 places. So to be like, you know, whatever words that were active, essentially. So it's similar to the one-hot encoding a little bit, but different. So almost your entire data set is zeros, but, you know, just some 1s or 2s if the word occurred twice. This type of encoding is called bag of words. It's like the most simple thing to do. So you have, like, there's certain, so that the way that data looks is very different than if you have like dense numbers that all mean something in every column. And so you end up choosing different algorithms. Like something like a GLM is probably what you want to use there, maybe a deep neural network. But if you have, 100,000 columns, you probably don't want to train a random forest or a GBM. So like these are things that you should probably think about when you're building an AutoML system. So we don't have anything right now to check for sparsity and to basically have a different pathway inside the program to do different things, but that's something that we will probably add at some point. So it's probably more common, I think, that people have dense data, so that's kind of the assumption that we make, is we will train a whole bunch of random forests, GBMs, deep neural nets, and GLMs. So one thing that we haven't added that we will is the ability to turn off certain algorithms in the AutoML process. So if you have sparse data, you just say, I don't want to do any random forests, I don't want to do GBMs, just do, or maybe just only do GLMs, and then it will train only GLMs. And so we'll first give the user the ability to do that, and then probably add some stuff to detect whether we should do that automatically, like maybe have a warning message or something that says, beware, like this is going to take forever to train this if you have 100,000 columns. So that's a good question. And other than that, we don't have anything, so we don't have any other assumptions that we're making other than like if you put time series data in there, that would not be good because we assume that the data is IID, which means independent and identically distributed. So time series is a very different type of data, and so we would probably want to either, build in that as like a separate thing, or maybe just have a flag if, let us know if this is time series, and then tell us which column represents the time date stamp or something like that. So most of what we're talking about here would be like non-time series type data. So yeah, another question? Yeah.
Is there a way to supervise the automated process? Like I remember you said like in the middle of that, like for Ensemble it works especially well on like individually strong models as well as uncorrelated errors, but like how do I know that? Like if I just throw it into this black box.
Well, that's part of like, so you don't, when you use AutoML, you don't have any control over really what it's doing inside. So we've decided all of that for you. So, so one thing that we're doing, so right now, it'll just train an Ensemble on all the models in the version that's out right now. So what we're adding right now is like, we're gonna do different subsets of the models and try to choose them in a smart way that you'll get maybe a better ensemble. So, so hopefully we'll cover all the different cases that, maybe we'll have 5 or 6 different types of ensembles at the end, and then whatever your data is, maybe one of those will work best, and then that one will pop up to the top on the leaderboard, and you'll just see, you don't have to know, like, you'll know in retrospect what happened and what each of these models are and how well they did, but you basically just let the AutoML process, decide all these things and do it for you.
What would be the best use case scenario for the AutoML right now?
Well, I think like the best use case is anything that if you want to just get a good model and you don't want to do all the tuning yourself, could be any use case, any machine learning use case where, so it's less, I guess, so it's somewhat about the use case. So we would assume probably you get the best results on data that was dense, maybe had like less than, 1,000 features, maybe 10,000 features. Doesn't matter how many rows you have, so I think, those are some basic things where this would excel. So if you have weirdly shaped data or sparse data or something more unique, you could try it and see if it worked, but maybe you would want to, look into what types of algorithms are good for that type of data and then train something yourself. But the good thing is you don't have to do any work to do this. So as long as you have a machine where you can run it, you could just say, maybe I don't think this is going to do well in my data, but I'm just going to give it a shot and just let it go. And if it returns anything useful, then I'll use it.
Only when the Kaggle competition, if the competition is the best case scenario for the AutoML, would you say?
Yeah, so the question was basically like, can we use this on Kaggle, I think. So one thing to note about this is that this doesn't do any feature engineering, at least right now. So the way that people win on Kaggle is two things. One, they do a whole bunch of manual feature engineering and like figuring out all these different new data sources that they can append to the data and stuff like that. So that's a lot of really manual work that in theory can be automated, and that's actually a different product that we're making right now that's called driverless AI that does that. But then the other thing they do is they do ensembles. So you need, I think to win at Kaggle, you need both. But if you, like, for me personally, I enjoy much more the modeling side of things versus the feature engineering things. So this is a nice tool for me. I just say, you know what, I'm just going to try this Kaggle competition. I'm not going to do any work. I'm just going to put this, so let this go and like see where it goes. Now that's probably not going to get you a great score because you're missing out on all the like feature engineering that people do. But the best way to use it is that you would do the feature engineering yourself, and then you give it to AutoML, and the AutoML thing does all the modeling for you. And then maybe if you're, want to take it even further, then you figure out like the best model that it took and kind of like look at what's in there. It's probably going to be an ensemble, so maybe this doesn't make a lot of sense, but you could try taking some of the models that it trained and try different ensembles or things like that. So yeah, and once we add some of the more advanced features to the stacked ensemble function in H2o, like the customized meta-learners or different meta-learners, which is probably in the next month or two, then we'll add that into AutoML as well. So then you'll be able to do all this stuff more automatically. So one thing that I might do if I were really trying to, right now, this version, using this on Kaggle would be take all the models and then do a stacked ensemble by hand using the GBM meta-learner. But I probably wouldn't do it because I'll just wait till we have it in the software and I'll do it that way. And it gives me a good motivation to finish that. But yeah, so this absolutely could be used on Kaggle. I would love to see somebody do a really good job of feature engineering and then do this and then get a good score. So we'll see if maybe somebody does that. Or maybe I'll do it, I don't know. Okay, any questions? All right, so that's, so I mentioned, the thing I didn't mention is, what is this thing at the end? So max runtime seconds, it just means how long do you want this to run for, basically. And there's 3 different ways that you can tell AutoML like how long to do its thing. So one is you just tell it a time-based thing. So you say, 10 minutes, go off and get some models and be done. Another thing is you can tell it the number of models. So you could say, train 100 models and then be done, or 30 models and then be done. The third way is a little more sophisticated, I guess. So it's early stopping for the AutoML process itself. So you keep track of the performance of the models in your collection that you're building, and then you kind of rank them in terms of like where is the best model and like how much am I improving by adding more models to this thing. So in early stopping, just in an algorithm, you say like you give it a couple different settings. So you have to control like how sensitive you want it to be. So you say like if the AUC of the model stops increasing more than some amount, let's say 0.001 after 5 iterations, then cut off the process. So you have we have defaults for that. So you can just say I turn on early stopping and hopefully it does something good. But if you want to control like how sensitive it is to the early stopping, so sometimes the performance can be a little shaky at the beginning. So if your early stopping setting is too big, it might it might stop too early. So you want to basically say, like, if after like 5 iterations of measuring the performance, if it still hasn't like increased, then stop or decrease depending on what you're looking at. So you can do that with AutoML as well. It just basically says if by adding more models you're not really getting much more value, then stop, essentially. So this is now what it looks like in Python. It's very similar. Our Python interface is a little bit more, Pythonic. It looks more like scikit-learn. So this all looks the same basically, and a lot of almost all the names of the functions are the same in our Python. So we have import file. So you make an AutoML object, and the only thing you would tell the object is, something about the run. So do 10 minutes or 600 seconds, and then you train. And when you train, that's when you tell it what to train on. It's that training set, and that column is your response. And then to look at the leaderboard at the end, it's stored there. And so first before we go to the leaderboard, this is what it looks like in our GUI. So the H2o GUI is called Flow. And you might not really be able to see this too well, but what I'll point out is this is all the same stuff that you have. So these are some of the hidden options that I didn't show on the other things. So we have the training frame, response column. This is the fold column, which you don't have to worry about. It's just we do cross-validation in this process. And so if you want to specify your own custom folds, like which row is in which fold, like some people want to do that or need to do that, you can do that there. I just added number of folds. So if you want to control the number of folds, it doesn't show up on this screenshot, but that'll also be there. If you have weights in your data, there's a way to tell it which column is the weights column. And then you can give it a validation frame, and we have something that we call the leaderboard frame. So this is kind of like a test set, but it's the test set that you score the data on to make the leaderboard. So right now, basically one thing it does right now is if you don't supply these things, the validation frame and leaderboard frame, it will just chop them off your data for you. So you don't have to split the data, although it's just like one line of code to split the data. But seed, that's just for reproducibility. Models to build, so that would be if you wanted to control the number of models, again, runtime seconds. And then these 3 have to do with the early stopping. So really, all you really need to do is this training frame, response column, and choose one of these to figure out how to stop it. Or if you don't set it, it will just run for an hour. And this is all, you can get this, I'll show you in a minute, but then you just hit the build model button. And this is kind of what a leaderboard looks like. So this would be for a binary classification model. It would show you what's called the AUC, or area under the ROC curve. That's just a metric that people use to measure binary classification models. So log loss is another metric people use. So we just show you both. We'll probably add all the metrics at some point. So this will show you the models in the AutoML. So typically the stacked ensemble wins. That's, if it's not, it probably means your data is really small. Sometimes that can happen. If you don't have enough data, it's, maybe if you have less than 1,000 rows, it would start to maybe slide down a little bit. But typically, if you have enough data, stacked ensemble will win. And then probably a GBM will be second. Like, based on my experience, then maybe, this stands for distributed random forest. Here's another GBM and another one. This is actually just the same as like a random forest, except for it's called extremely randomized trees. It just means it's more random than a random forest. It's just a version of random forest that does well sometimes.
Is
so
that a new thing in H2o?
It's not its own function. You can do that through setting different things in either the random forest function or the GBM function. If you we should probably make a wrapper that just sets those things. So if you want to just say train an extremely randomized tree forest, then just do that. But yeah, if you look in our user guide, it'll show you like what the parameters that you need to. Yeah, it's kind of, I think if you read either the random forest or the GBM, I forget if it's on both pages, but it's on one of those pages, it'll say something at the FAQ or something at the bottom that says like, you know, how to train an extremely randomized tree. So yeah, this, like in this example, I don't know, we have like less than 10 models here. So GLM pretty much always does the worst. That's okay. One of the things that we're adding is an ensemble that leaves out the GLMs, because as you can see, they're quite different in terms of their performance compared to these other models. So if you look at the numbers in terms of AUC, these are at 0.68, and then it jumps up to 0.72 is like the next one, 0.73, 0.73, 0.73, 0.75, and then 0.77. So these are actually much worse than the tree-based models. So sometimes I've seen that if you put too many really bad models in an ensemble, it's not a good thing. So we have added a version of the ensemble. So in future versions of H2o, there'll be multiple stacked ensembles that do different subsets of the models. So there won't just be one.
I'm surprised not to see deep learning in this, or is it?
Yeah, I forget, like, this might be just a screenshot from something either where deep learning wasn't working yet or it skipped it. Because if you don't, it's supposed to sort of distribute the time in not evenly among all the different models, but in a way that we specify. So we're going to say, because you can train so many GLMs in the amount of time that you could train one GBM. So we don't say like, give equal time to the GLM grid. We say, give a little bit of time for that because it doesn't need that much. Give deep learning a little bit more time and give like, you know. So we, you know, proportion the time in a way that we think is sensible. I don't know why this one is missing the deep learning. We'll see if when we train it, like right after this, we'll just run it once and we'll see if it pops up. And so this is a slide, like if you want to just take a picture of this, if you're trying to like get a bunch of resources, this is where we have all of our stuff. So docs, documentation, the user guide is in there. That's the best place. We put all the tutorials that we have, like just code tutorials of different things are here. All the slide decks, including this one, goes here. Video presentations, including this one, will go on our YouTube page. And then this is just I think this page is still relevant or active, but we list a bunch of our events. So we do mostly meetups, but then there's also conferences and other things that we do. And if you want to get a hold of me, this is where to find me on GitHub or Twitter, and that's my email address and my website. At some point, I'll get a new website, but that's my Berkeley website. Okay, and so then quickly, we're just going to, so maybe we'll just pick one language. Are there more Python or R people here? So Python, raise your hand. Oh, I think that's going to be the winner. Any R people? Yay. Take an R Ladies sticker when you leave. I brought some R Ladies stickers. I don't know if there's Pi Ladies, R Ladies. There are these groups, women in tech. Anyway, no R Ladies in here, though. OK, so let's do Python. So I'm going to show you. So this is our slide deck page. So what I'm going to do is just show you how to get to the documentation, because that's where the code is that you're going to run right now. So if you go to docs.h2o.ai, scroll down, and H2o user guide. So this is in bold so that you can find it later. But yeah, this is the user guide. And now we're going to go down to AutoML. So just describe it. It talks about the different parameters. And if you scroll down far enough, you'll see code examples. So we'll click on Python. And we're just going to paste these into a terminal. Oh, and I should also mention, well, how do you get H2o? You can either, in Python, you can pip install H2o. But I will warn you that if you do that right now, you will not get AutoML in there because that version is behind. So I know, it's really makes me mad. But there was an issue where PyPy has a limit on the size of the wheel file, and we have exceeded that. And so now we are working to get that limit increased so that we can put our, not just like for us and like increase. So if you ask, I guess if you ask nicely, they will increase it for you. So we have to do that. But if you want to, you can always get it from our website. If you do h2o.ai/download, it's probably.
I have a question while that was.
Yeah.
Can you control which version you get? Because it was like the sub ... versions, if you didn't have them exactly matching, they would not work. And it was like, I couldn't figure out how to control it.
Yeah, so one thing you can do if you have you see like a version mismatch error, is that what you were seeing?
I had a version mismatch error, but it was like on the, the third decimal place.
Yeah, so
and I couldn't.
There was
no directory to go to.
Yeah, so one thing you can do is there's an option in the h2o.init function that says strict version check. If you set that to false, that's a loophole. But if you really want to find the right version, well, usually you would go here and you go latest stable release. And then if you want to install in Python, this is how to do that. But our release pages are versioned, so if you know the release that you're looking for, then you can just type the URL in that you know that it is. Otherwise, you can, if you don't know exactly the name of the release and all that, you can go GitHub and go to H2o AI is our GitHub name, and then if you go to H2o3, that's H2o. And then if you go to changes.md, that'll show all the changes for all the different versions, but it also has a link to the download page for each version. So if you're like, oh, I really need, version 3.12.0.1, hopefully you can find that and then go to the link on that page. But if you're, in Python, just install from here, you'll be fine. So now I've already installed H2o. Okay, so let me make that bigger and bigger, bigger, bigger. So I'm just going to use IPython, and so I'll do import H2o. And I'm just going to go back to, where were we? Go back here, and I'm going to just copy paste all this stuff. So we import H2o, we import some training and test data. The way that you tell H2o which columns, like what is the response column, we call that Y. If X is actually a list of the predictor columns. If you're using, basically, usually people have a data set where one of the columns is the predictor and then everything else is, one of the columns is the response and everything else is the predictor. If you need to remove an ID column or something like that, you can specify which ones you actually want to use in X. Otherwise, you can leave it blank and it will just assume everything else is predictor.
That's I found really handy. A lot of systems aren't as easy to do.
Yeah, so try to make everything as easy as possible. So this will, So first what you're seeing here is this is just some printout that's like when you start up an H2o cluster. So this is just on my laptop. It prints out some information like the, the version number. This version was released 24 days ago. Here's the number of nodes. So we're on a laptop, so one node. By default, it will give you a 4 gig cluster, but you can specify how much memory you need. And usually, you can play around with that. Like, if you have more memory, just give yourself more to use. And then, if you need to be more sparingly, you use it more sparingly, then start small. And if that's not enough, then increase. Then it'll show you how many cores you have. And then I just also pasted to get the data in here. So now if we do, so what this will do is it will run AutoML for 30 seconds. And then we will sit here. And if anyone has any questions, now is a good time to ask.
Does the H2o init show you GPUs? Because the one I used last, it didn't.
So there's a integration that we call deep water, which is kind of like a separate thing, but there's a function that will check if you have GPUs, but that's specifically for deep water. But I think also if you're using XGBoost, there's a function that checks if you have GPUs, and it will use them.
So is the AutoML also in deep water, or is it just?
We don't have deep. So what deep water is a wrapper around TensorFlow, Caffe, and MXNet, which are 3 deep learning libraries. But yeah, so that's not something that we've put in AutoML. We might at some point, but we also might not, because it's typically if you're using those types of libraries, you have different kind of data. You don't necessarily use that on numeric dense data, which is kind of what this is designed for. Maybe you have images or time series data or something like that. So you can use those libraries to do deep learning on this type of thing. But if your data is dense numeric data, you probably could just use H2o's deep learning algorithm, which is just called H2o.deeplearning.
Switch between the two easily?
Yeah, that's kind of like the point of deep water, was to make it easy to, if you're already living in the H2o ecosystem, to just using a different function, H2o.deepwater, to try out these other libraries. But if your goal is you're only using TensorFlow and you already know what you want to do, you might as well just use TensorFlow, So it's kind of meant for if you're doing multidisciplinary work, where sometimes you might want to use a deep neural net, and sometimes you might want to do a GBM. That will allow you to do that. But a lot of times when people are using a TensorFlow, they have a particular type of data that's you need TensorFlow or something like that for, and it wouldn't work on an H2o GBM. So it just depends what you're trying to do.
Well, I guess what I'm wondering, sorry to dominate this, but there's a separate download for deep water, there's a separate download for the other pieces. So how, when you say H2o init, how does it know which one you want?
So if you use the deep water bundle, it's you'll be using an H2o that knows about deep water because it's already installed and available. So if you don't have the deep water version of H2o, then it doesn't know about it, basically. It's kind of like an extension package. So if you look at when we started H2o, you see there's some what we call extensions, and you don't see deep water there. And I don't remember if deep water, if it shows up as an extension when you use a deep water enabled version, but it is a separate distribution. So we have functions built into the H2o to access the deep water, but if it's not there, then they don't work, basically. So there's an H2o.deepwater function, but if you're not using the deep water version of H2o, then it doesn't do anything. And the reason that we do that is because these are huge libraries to bundle with H2o. We don't want to like smash everything together if you don't need that. And most people don't, so we don't need to deliver the entire deep learning like universe as part of regular H2o. Okay, so let's just look at the leaderboard. So basically what we have here is we've trained 7 models and so six base models and then 1 stacked ensemble, and we find that stacked ensemble is doing the best. And then we'll see that, this particular GBM is this, whatever. So if you want to look and see, like, what was that GBM? Like, what were the settings? You can do H2o. So these are model IDs. So if you do get model, that'll bring the model, like, so you can do stuff with it. And then let's see, this might give me way too much information, but this is like all the values that correspond with this particular GBM. So like things you might be interested in are, sample rate, that was 0.8, So this is, if you want to like kind of learn more about what parameters do well and kind of study this data, you can look at this. Another thing that I would actually recommend doing is maybe, let me just show you one thing real quick. In the docs, or no, sorry, this is a tutorial. So if you're just learning about H2o, I would recommend that you go to GitHub and our H2o-tutorials repo. And if you scroll down, it'll show you kind of like, there's a bunch of tutorials in here, but if you're just learning, like, try some of these. So if you're Python, you go, let me find out, how do I do grid search in Python? And it will show you a notebook. It shows you how to do that. And the reason I'm going here right now is I want to scroll down to the end where if you print out a grid, the whole grid, it'll show you something more nice like this. So it shows all the grid values and then the name of the model and then the performance. So this is actually a little bit inconvenient how this is formatted because the performance metric is on the next line, but these are ranked by like how good the model is. So interesting, that was the same sample rate that we found in the AutoML model, 0.8. Maybe that's a good value if you keep seeing that doing well, but it's totally dependent on your data. So I would not read too much into this and say, oh, sample rate, 0.8. I'm always going to use that. It's the best one. And if you're wondering what that means, in a GBM, every time you build a tree, you sample some subset of the rows. And this is just saying that percentage is 80% of the rows. Anyway. So go there if you want to learn more. Anyway, that's what AutoML does. So it's gone off and it's done all this stuff that you would actually typically learn how to do this way. If you're just using the grid search functionality directly, what you have to do is set up all these values. That's kind of hard to do if you don't know anything about GBMs. So you might not, like, what does max depth mean? I don't know, like, should it be 1,000,000? Should it be 100? Like, these are things that you learn as a data scientist. Like, GBMs, like, typically you want somewhat short trees versus a random forest where you want deeper trees. Max depth might be different. Like, these are all things that you learn as you, progress in data science. But this is hard because if you don't pick the right ranges, you're not going to get the best models. And so we try to pick good ranges for our grid searches so that you don't have to. And this is how you would train a grid and do it all manually. So this is all stuff that we're doing under the hood. So anyway, that concludes our session. Let me just show you, I did mention that I would show you how to do this in Flow, but basically I just want to point you to where it is. So if you go run AutoML, it'll bring up this thing. And I've already run AutoML, so there's actually a bunch of frames in there, so it's kind of confusing, but here's the one that's the training set, and then I would say, like, what's the response column? There it is, and then you say, run that for 20 seconds, and hopefully this will work. I haven't done this recently. And then now we're training in Flow, so no code at all. And it kind of gives you a little, I guess, update about what's going on here. So it's training some GBMs. This will be over in 10 seconds, hopefully. Okay, we're done. Now we can like view the leaderboard. Oops, I forgot to, I used the wrong data set, so it actually thinks that we're doing a regression problem, so we see different metrics up here. So one of the things that we did in the Python code was convert the response column, which was encoded as zeros and ones, into a factor. So that's how you tell H2o if you want to do regression versus classification. It has to be a factor or categorical column. Otherwise, it thinks, oh, zeros and ones, those are numbers, I should be doing a regression. So this is how you tell H2o, do you want to do regression? Or a lot of times your data is encoded as a factor already, so it might be like yes and no, and so it automatically does the right thing. But that's why you saw a different model there. Okay, so thank you very much for coming, and I'll leave this resource website up here for anyone that needs it. Thanks.